from the University of Toronto, who is going to speak about the generalized TAP free energy.
Okay, this is a joint work with Wei-Kuo Chen and Eliran Subag. So I'm going to talk in the setting of the same model as Francesco was talking about. So we consider a Hamiltonian with Ising spins, -1 and +1. And the model is, of course, defined by the fact that it's a Gaussian process with the covariance given by a function of the overlap, which was a square in the previous talk. For general mixed spin models, it will be some mixture of p-spin models, so the function of the overlap can in principle be some sum of inverse temperature parameters squares x to the p, corresponding to the p-spin terms, like this. So I will call psi the model. It will appear in all the formulas. And one more thing that will appear that I will mention from the beginning is we have this, of course, for this model, we have the Parisi solution, we have the Parisi formula, and everybody knows about the functional order parameter of the model. So the zeta will be a functional order parameter as a variable, and zeta star will be the optimal one in the Parisi formula. Okay, so I want to talk about the generalized.
What is capital R?
Capital R is the overlap between these two configurations, sigma 1 and sigma 2. Okay? So I want to talk about the generalized TAP free energy, so I need to define the TAP correction in the TAP representation and the corresponding TAP states. So the motivation for the definition, which already appeared in the work of Eliran Subag on spherical models, is the following. The motivation comes from the Parisi solution. So in some sense, Parisi solution came after the classical TAP free energy representation. And here we take it as a motivation. So what do we know about the Parisi solution? Well, we want to define the generalized TAP states, which include ancestor state at every level of the overlap or self-overlap. And ancestor state, if you visualize the ultrametric Parisi tree, they have the property that at every ancestor state, you can go in many orthogonal directions to reach many pure states, which are all in orthogonal direction relative to their ancestor state. So if you take a point inside the hypercube and you know it's an ancestor state, you should have the following property, right? So if I just put in formula what I just said, you take a narrow band, what we'll call a narrow band around this point, which is just all directions. So all configurations of spins such that the step from ancestor state to sigma is perpendicular to M. Now, of course, you have to write everything with some error. You want to take a narrow band with some epsilon parameter, but for this talk, I will write everything, a little bit heuristically, approximately. So you should say, you should think about this as approximately perpendicular directions from M And the fact that I want to find many orthogonal pure states means that I want to look at many of these orthogonal steps at the same time. So I'll define this set Bm with index n. Sorry. As a set of, well, think of little n number of replicas in this narrow band such that all these steps are perpendicular to each other. So sigma L minus m is approximately perpendicular to sigma L prime minus m. And again, you can, in general, put some small parameter delta that controls in the definition. And then, if you write that the free energy is bigger than the free energy with the constraint that you are in this band, so instead of summing all configurations, you sum over the band, you get an inequality. Of course, you know that if you are in the ancestor state, this is an approximate equality because you pick up some pure states in the band. So you don't lose, you don't see it at the level of free energy. Also, the infinitary nature of the Parisi solution means that even if you restrict or even if you consider replicated free energy with these constraints, of course, by adding additional constraint on this n replicas, you decrease the free energy. But again, you know that if m is an ancestor state, you didn't lose anything because there are many pure states in these possible orthogonal directions. Now, if you just rewrite this like in a typical TAP representation by adding and subtracting the energy at the point m, well, you get the same kind of replicated free energy just for the model recentered around m, okay, by subtracting the energy at m. And typically, in the classical TAP representation, you write free energy is the supremum over TAP states of this guy plus some TAP correction. And here, for the moment, we'll call it a TAP correction, which for now depends on this number of replicas that I chose and depends on m, so, and it's also random, okay? And I want this to be basically an analog of the TAP correction in general, okay? I want to be able to detect which points inside your hypercube do not feel these constraints, okay? It doesn't mean, of course, because we are looking at the level of free energy, it doesn't mean that you do have pure states in the orthogonal directions if you have approximate equality, but it means that, you know, at least at the level of free energy, at least this includes the ancestor states, okay? Now, what is the point of this definition? Well, the point of this definition, there are two, you know, I'll call it pros just to make it, put some emphasis on this, that why do we want to use this infinitary nature of the Parisi solution and the fact that we know that ancestor state would give you approximate equalities? Why do we want this n, the number of replicas here, to be large? Well, the main point that is used in what we are doing after this is that the self-averaging, you know, Francesco just talked about the self-averaging of the free energy. This is also free energy of a model on the band with replicas and some constraints on the replicas. Now, this free energy, the self-averaging if you look at it, it gets better with the number of replicas. So with n going to infinity, the self-averaging gets better. You can just check it the same way you check the self-averaging in the usual case. And then the crucial point for us here will also be the external field becomes irrelevant when you use the fact that the number of replicas is getting large. Okay? What I mean by that is that, first of all, here in this recenter model, there will be a first order term which looks like an external field. Or if you add, sorry? If there is an external field, it will disappear with number of replicas going to infinity, because, just by Pythagorean theorem. Because you sum over many orthogonal directions, external field will be killed by the sum of the orthogonal directions. Okay? Just by Pythagorean theorem, it will grow like square root of the number of replicas, while here you have n. Okay? It becomes irrelevant. So that's another important point. Why do we want to look at many orthogonal direction and take it as a definition motivated by the Parisi solution? You can add external field here, and it doesn't change the quantity at all for large n. Okay? Now, of course, again, it's not really cons, but for some kind of emphasis, I'll call it cons. You can say, okay, looks like, at least a priori, this depends on the number of replicas. Does this depend on n? And B, can you calculate this quantity that you want to use, right, to detect your ancestor state or, ancestor-like states? Well, let me state as a theorem, what we get is the following: that with high probability, uniformly over all m, so you're testing, first of all these points at the same time, rather than one by one, this tap correction will be independent of m, and it will be some explicit formula that we will calculate when n goes to infinity, when n gets large. Okay? And this part here, the fact that we can do all simultaneously, is a consequence of the self-averaging getting better with n. So the self-averaging control wins over the entropy of this box, n-dimensional box. And we can calculate this because we can play around with external field. Okay? And as a result, this will be called generalized TAP correction. Okay? And automatically you get the generalized TAP representation, okay, which I will state maybe one more time later, but yes. Well, I traveled light, so I didn't print out. You can.
So, uppercase n equals to infinity and then lowercase n is constant?
No, you fix, this is exponential in n. You fix a constant here, whichever you like. You fix any error here that you like, and then you say there exist small epsilon and delta in the definition of these sets, and there is fixed large enough n that this is true. Okay? Something like that. So if you want this to go to 0, it will, epsilon and delta and n will go to infinity with it, but you can give a statement for a fixed with arbitrary accuracy. Okay, let me write down what the formula for this is. Okay, so you take your order parameter, as usual, distribution on 0, 1. And I'm going to start writing basically what looks like a Parisi formula. So you start with this usual function where you solve Parisi PDE with the boundary condition log of 2 hyperbolic cosines of x. Then you solve the PDE. Okay, let me write it quickly. You're all familiar with it. Right? You write this PDE, you write some functional. Now there is extra step here. We have a functional. We have to take this concave conjugate of the Parisi, the nonlinear Parisi functional, the first term in the Parisi formula. You take its concave conjugate. Okay, as usual, Q is the overlap parameter between 0 and 1, and this variable in this definition is between -1 and 1. That's like a magnetization, the meaning of magnetization. Okay, and then the rest is very much like the Parisi formula. Now we call it a TAP functional instead of Parisi functional. You apply it, you apply this functional, and zeta is again the order parameter here. You apply it to the coordinates of your ancestor state or TAP state. And then the usual linear term in the Parisi formula, where this Q is the self-overlap of the state that you're looking at. Okay, it's just the self-overlap of M. Okay. And then the TAP correction is just like the Parisi formula. It's the infimum over order parameter of this TAP functional. Okay. Now notice here that if you look in the definition, it only depends, on the values of this order parameter starting from self-overlap, so from Q to 1. So it doesn't really depend on the values of the order parameter from 0 to the self-overlap, so I didn't need to include them just for some kind of consistency. So it applies uniformly for all Q. I hide it in the definition. Okay? And so you see, it's basically very similar to the Parisi formula. Okay? Look at it for a second. Okay. No, you don't. All right. Now, since you see that the main difference is here, by taking a concave conjugate, that's the new thing. So you can say, where does this come from? Well, that's where the main point appears that I mentioned here. You have to play around with external field. So the meaning of this infimum over x is, well, there is a simple part. It just comes from, first of all, just a large deviation, removing the constraint that you are on the band. But the more important is that it corresponds to finding good external field which, by the way, will be of the form, external field will also depend, it will change with the coordinate, and it will be of the form some function of the corresponding coordinate of your state. Okay, so it will be like this, so it's really looking for this function that defines the external field. And the point, of course, what is the point? The point is that when you look at this free energy, it's a replicated free energy. So first of all, if you want this to be independent of the number of replicas, you have to make sure that the constraint here doesn't play a role. The constraint means that the overlap, this just means overlap between these two configurations of the model on the band are perpendicular. So it really means that for this model on the band, the overlap should be allowed to take value 0. If you can make sure that the overlap is allowed to take value 0, of course, then you can forget about replicas, and this becomes just a free energy of the model on the band with that external field. Okay? Well, can you find this external field? It turns out that there is a very more or less simple necessary and sufficient condition for the 0 value of the overlap to be allowed, right, in the model in this sense. And for some of you who might have heard my talk last year in Cargese, the searching for this external field, at that time, it was an implicit, I mentioned this is some kind of implicit fixed point problem, because you have to optimize, you have to optimize over your usual order parameter, but at the same time, you have to look for this external field. So luckily, since then, we made a lot of progress, and this was solved much more explicitly, so that the external field, we can include it in the variational representation, so you you optimize simultaneously over both external field and the order parameter, and that automatically ensures the condition which is equivalent to 0 to be in the overlap. So that's one lucky thing that simplifies. Another one is that when you remove the constraint of being on the narrow band, you get some different boundary condition than in the usual formula with log of hyperbolic cosine, because your spin is now shifted by m. It's 1 minus m or minus 1 minus m. Now, luckily, the Parisi functional with that boundary condition is related to the classical one in some simple way. So in the end, all things simplify, and you get that all you have to do is just do this one more operation, right? That really corresponds to these physical steps that I tried to explain. So in some sense, this representation is very non-physical. The physical steps algebraically disappears because of different simplification, but you get a nice simple formula that now you can play around with. Okay? And I think I started a bit late, so I still have about 10 minutes, right?
No.
Okay.
No. You did not start late. You started 10:01. So you really have 5 minutes.
All right, so again, if you remember one thing from this talk, you should remember that the generalized TAP correction is nothing but a Parisi formula for a model on the band with a special external field that makes sure that 0 of the model on the band is in the support of the overlap of the functional of the order parameter. Okay, now because you have this explicit formula, you can play around with it. Sorry, I'm really dehydrated because of the jet lag. So sorry, I keep drinking. That also takes time. Apologize. But it's not worth flying from North America to here for 30-minute talk, right?
It's a kind of replica trick you are playing. Just go on.
All right, sorry. So, well, let me mention maybe a couple of things that you can do with this formula. First, I said that ancestor state by definition a tap state. And of course, what is a tap state? A tap state is just a maximizer of the energy plus, instead of this, the thing that we calculated. But on the other hand, we can check that if M is a tap state, although tap states spuriously may include non-ancestor states, the order parameter, now when you minimize in this definition, where is it? In that definition, let me call the optimal value of order parameter for the tap correction zeta m. It turns out that it has to be the same order parameter that in the original model. So the order parameter for generalized tap states look like the one in the ancestor states. Okay? Now, moreover, although the formula looks complicated, for tap states, you can calculate explicitly what the energy and the correction will be. Okay, so the energy will simplify, if you like, to some very simple explicit formula. Like this, okay? So all tap states corresponding to self-overlap. Now I have to add that we only take values of the self-overlap which correspond to physical ancestor state in the model. So they should be coming in the support of the functional order parameter of the original model. Then you can calculate the energy and the tap correction more explicitly. And then you can also calculate the tap equations. So the tap equations for the critical points look all very similar to tap equations in the classical case. Now remember I said the order parameter is about the same, so you can change the order parameter to the classical one if you like. And then if you also want, you can compare it with some results in the literature. For example, there is Mizard-Virasoro equations for ancestor states which were generalized from two-spin case to the mixed p-spin case by Aufinger and Jagannath, okay, which look, sorry to erase right away the names, but let me just write it next to each other. It looks very similar with the exception that this term is something different. The physical meaning of what is going on in those representations is different. And this derivative goes inside the integral with a variable. Okay. And the physical meaning, of course, for the SK model, the second derivative is constant. So it's the same thing. The equations are the same. So what Mizard and Virasoro did in their paper is the same thing for that case. But for mixed p-spin model, it's not the same thing, because the physical model of what is being looked at here is the cavity process in the Parisi solution, which basically is not the gradient at this point, but it's the average of the gradient over many of these orthogonal pure states. And when the gradient is not linear, these two are not the same. So here we get true TAP equations for, well, these generalized TAP states that we defined. Okay? Finally, I'll just answer the question that Federico asked. You can say, what is, when this becomes the classical TAP correction? Well, that corresponds to the case where the optimizer, the variation of the autoparameter in that optimization problem becomes just a delta function at 0 for the model on the band. Then it becomes exactly the classical case. And interestingly, it's not always true that this Parisi formula for this model on the band is equal to the classical one when you are on the Edwards-Anderson sphere. Okay? Now, of course, it's also true that the TAP representation is still true with the classical one. It's just that the classical correction doesn't have the same clear physical meaning for all values of this on the Edwards-Anderson sphere. And in particular, there is this well-known Plefka's condition in the literature. It becomes the analog of the AT line. So the Plefka's condition is a necessary condition for this to be a classical correction, but we don't know if it's necessary and sufficient, but at least it's an indication that Plefka was on the right track. Now finally, there are all of these analog of all these results at 0 temperature, except for technical reason we don't have the analog of this very simple formula for the energy. Okay. And maybe final 10-second statement is that for the same reason, I think what Andrea is going to talk about in his talk, I think for the same reason that the gradient is nonlinear, okay, when you try to generalize this AMP calculation that Andrea does for the SK, it doesn't look that it's automatic, technically at least. Okay, I haven't thought about this too long, but you can say, what is the update rule in this case when the gradient is not linear? When you just work with the same random matrix at every step, you have to decide at which m you evaluate previous, or m-2 or m-3, and then of course you have to redo the whole theory of the AMP calculation. But so that's another interesting problem related to the general case here. Okay, and now let's stop. Sorry.
I don't think we really have time for a question. So still, okay, Miguel?
Yes, just a very late question. I understand. Let me take the spherical speed because I don't want to get involved in this the correction. In the spherical speed, you are saying that that correction is another Parisi formula on the band.
And it just becomes the classical one because the band is another sphere. Yeah.
If we do the same trick there and try to find a TAP solution for that particular band, that is to maximize or minimize an energy, and then somehow,
Well, the TAP,
two TAP equations. I mean, the TAP equation for
the TAP correction is constant for the spherical case on the sphere. It doesn't depend on the location by the symmetry.
There is no replica symmetry breaking in the
No, there is, but the correction does not depend on the point, right? The TAP representation is just energy plus the same quantity for all points on the same sphere. The correction does not depend on M. TAP of M depends on M only through its self-overlap.
Okay, but I was referring to the second. I mean, you're saying that there is we have to solve.
Autoparameter,
We have
yes.
to solve a new system
Right,
on n-1 dimension.
Yes.
That system, couldn't we solve it using a TAP equation?
I mean, you don't solve anything using tap equation.
Well, I mean, I know, but I don't, it's another representation.
Sure, yes, you can. You're sure you can. Yeah, yeah. Yes, you can. You can, and you can iterate if you like.
Yeah, that's,
Yes.
could it be, perhaps it could give us some ideas on the electricity or whatever. I mean,
It's right now it works the other way around, but you know, you never know. I mean, that's for the future generations. I'm close to retirement, so.
Okay. I think, Mark, a very quick question.
Just one small question. Actually, in this paper with Miguel that you mentioned, we were elaborating a way to compute the correlation between magnetization in various states. And from that, you can deduce the tap state by averaging over many descendants, as you do, let's say. How many states which are descendant from the same ancestor.
Okay.
But then we get something more generalized. We can have mixed correlation between configuration trying this
sure.
ancestor,
Yeah, yeah.
another
Yeah,
ancestor,
yeah.
and so on. So I was wondering if you're generalized to these kind of more elaborate things, not only concentrating on one ancestor, but the correlation between an ancestor and another state which is far away as well.
Well, this works for all m. I mean, here we give a statement for all m. It depends what you want to do. I mean, what you are doing is, yeah, of course, you have this explicit description for this cavity field on the whole tree. So you calculate at any two states in a pretty straightforward way. But I don't know what you want to do here. But you have a statement which is true for all m everywhere. So you can deduce from whatever you like. I mean, it could be an interesting question here because at least for tap states, there is now clearly a relationship between the gradient and the average of the gradient over many pure states, right? It's written right there that one is a function of the other. So it could be an interesting question to look at this as an abstract question. By looking at the cavity field process, can you recover the gradient, even when the gradient is nonlinear, right? So this could be another interesting problem.